Hello. This lecture, it's going to be will be in two parts. The first part, in both of them, we will be talking about the introduction to Internet of Things. Um, in this part, I will be introducing and or defining the Internet of Things, talking about different terminologies, a terminology that's related to the Internet of Things. Okay. So, again, welcome to the world of the Internet of Things. Internet of Things is a network of physical objects, anything from your phone to industrial sensors that are connected to the internet that can collect and exchange data. This means you can monitor and control these devices remotely using existing networks like Wi-Fi and cellular. Internet of Things bridges the gap between the physical and digital world, leading to improved efficiency, accuracy, and economic gains. Let's go to the next slide. In this slide, we'll continue the definition of the Internet of Things. Internet of Things is not just about your phone or computer. It's a vast network of everyday objects, from medical implants to smart appliances that are connected to the internet. These devices are equipped with sensors that allow them to collect and share data autonomously. This opens up a world of possibilities ranging from remote health monitoring to smart homes and beyond. The Internet of Things is shaping the future and it's getting started. It's just getting started. Let's take a look to some history or background about the Internet of Things. The Internet of Things, or IoT, has a rich history dating back over a century. Our journey begins in 1912 in Chicago, where a pioneering system used a telephone lines to remotely monitor data from power plants. Power plants is it's shown in this picture. This early example of telemetry laid the foundation of the technology we know today. Fast forward to the 1930s, where telemetry expanded into meteorology. The invention of radiosnet, a device carried by balloons, allowed scientists to gather weather data from atmosphere. This marked a significant step forward in our understanding of atmospheric conditions. And this is shown here in the second picture. Then came 1957 and the launch of Sputnik by the Soviet Union ignited the space race. This event spurred advancements in aerospace telemetry, which became crucial for spacecraft navigation, communication, and data collection. The technologies developed during this era paved the way for the global satellite communication networks we rely on today. And we can see this in this bottom picture. The Internet of Things is a testament to human ingenuity and a journey of continuous evolution. From monitoring power plants to exploring the space, telemetry has shaped our world in countless ways. And as technology continues to advance, the future of Internet of Things holds even greater promise. We continue with the history. The Internet of Things has, like I said before, a fascinating history. Its roots can be tracked back to 1999, when researchers at MIT's Auto ID Center envisioned a world where everyday objects and even people could be equipped with unique identifiers. These concepts, driven by the potential of radio frequency identification, RFID, aim to revolutionize how we track, manage, and inventory things. While RFID remains a crucial technology, the Internet of Things have evolved significantly. Today, it encompasses a broader range of identification methods, including NFC, that stands for Near Field Communication, barcodes, QR codes, Bluetooth, and digital watermarking, coupled with the advancements in sensors, connectivity, and data analytics. These technologies have fueled the rapid growth and widespread adoption of Internet of Things that we see today. The Internet of Things is transforming the industries and our daily lives, from smart homes and wearable devices to connected cities and industrial automation. As technology continues to advance, the future of Internet of Things holds even greater promise, shaping a world where the digital and physical realms seamlessly converge. The question that could arise, why Internet of Things now? So, why is the Internet of Things exploding right now? There are several key factors driving this rapid growth. First, ubiquitous connectivity. 5G and beyond are delivering blazing fast speeds and ultra low latency, enabling real-time data exchange for mission critical Internet of Things appliances. Second, the widespread adoption of the Internet Protocol. This standardized foundation this standardized foundation ensures seamlessly connectivity across the diverse Internet of Things devices and networks. Third, computing economics are becoming more favorable. Edge computing and cloud solutions offer powerful promising and storage capabilities at increasingly affordable costs, making Internet of Things deployments scalable and cost effective. Fourth, advances in data analytics are unlocking valuable insights from massive Internet of Things datasets. AI and machine learning algorithms are optimizing operations, driving predictive maintenance, and personalizing experiences. Finally, the rise of cloud computing provides the scalability, flexibility, and agility needed to manage the vast amounts of data generating by Internet of Things devices, enabling rapid, rapid innovation and deployment. These factors combined are creating a perfect storm for Internet of Things growth, and it's clear that this technology is poised to revolutionize industries and our daily lives in the years to come. In this slide, we meet the Raspberry Pi Zero, a tiny but mighty single-board computer developed by the Raspberry Pi Foundation. This little guy is known for its incredibly low cost, typically around $5, making it a popular choice for makers and educators. The Raspberry Pi is packed with features. Despite its size, it's capable of running full operating systems like Linux, allowing you to do everything from serving the web to controlling robots. Its a small size and affordability make it perfect for DIY projects, education experiments, and even building your own custom computers. With Raspberry Pi Zero, the possibilities are endless. So whether you are a seasoned maker or just starting out, this little computer is a great way to explore the world of electronics and computing. This complex landscape showcase the diverse range of players and technologies that are driving the Internet of Things revolution. First, platforms and enablement. Platforms and enablement. At the core are the platforms that provide the foundation for Internet of Things solutions. We, s- we see names like IBM, Cisco, and Honeywell offering connectivity, data analytics, and application development tools. Applications. Now, let's dive into the vertical applications. We have a quantified self where devices like Fitbit and Withings track our health and fitness. In the connected home, we see smart thermostats like Nest, smart lighting, and security systems. The industrial internet is transforming and manufacturing with the predictive maintenance, remote monitoring, and automation. Building blocks. These are the fundamental components powering Internet of Things. We have connectivity options like Wi Fi, Bluetooth, and cellular networks. Then there are the protocols that enable communication between devices. And of course, the hardware, which are the sensors, microcontrollers, and ever popular Raspberry Pi. Software platforms. This layer includes operating systems and the development environments that run on the Internet of Things devices. We see open source platforms like Arduino, and OpenHub alongside commercial options like Microsoft Azure and AWS Internet of Things. Funding and distribution. Funding and distribution. Let's acknowledge the ecosystem financial backbone. We have venture capabilities and crowdfunding platforms that fuel innovation. And then there are the distribution channels, retailers, online marketplace, and even the emerging concept of the Internet of Things store. This interconnected web of technologies and businesses is constantly evolving. New players are emerging, new applications are being developed, and the potential of internet for the Internet of Things to transform our world is limitless, as I mentioned multiple times before. In this slide, we I wanted to highlight that Internet of Things is not just about connecting devices. It's a convergence of several key technologies working together to blur the lines between the digital and physical worlds. First, we need seamless connectivity. High bandwidth networks like 5G and Wi-Fi 6 provide the foundation for reliable and low latency communication, allowing Internet of Things devices to exchange data in real time. Next, we need universal addressability. Every Internet of Things device requires a unique identifier, like an IP address, so it can be located and addressed on the network, enabling smooth communication and data flow. Security is paramount. Robust identification and authentication protocols are crucial to ensure the trustworthiness of the Internet of Things devices and the security of data transmitted across the network. Then we have intelligent sensing, a diverse array of sensors from temperature to motion to light gathers data from the physical world, providing valuable insights into environmental condition and user behavior. Precise actuation enables Internet of Things devices to respond to data and interact with the physical world. This could involve controlling lights, adjusting thermostat, or even triggering complex actions in industrial settings. Embedded processing power within Internet of Things devices enables local data processing and decision making, reducing latency and improving efficiency. Accurate localization. Technologies like GPS, Wi-Fi triangulation, and beacons Bluetooth beacons enable precise location tracking of Internet of Things devices, enabling location-based services and enhanced user experience. Finally, intuitive user interfaces make it easy for people to interact with and control Internet of Things devices, maximizing their value and adoption. These technologies working together are powering the Internet of Things revolution, transforming industries and creating a more connected and intelligent world. Now the question becomes how the technologies we mentioned in the previous slide work together in Internet of Things. So let's see how these technologies work together in a real world scenario. Imagine a smart home. Sensing, temperature and humidity sensors in a room collect environmental data. This data is transmitted over Wi-Fi to a central hub or the cloud. The thermostat, identified by its unique address, receives instructions from the hub. As part of the accommodation, the thermostats adjust the temperature accordingly. The temperature might also analyze historical data and adjust temperature settings proactively. This is part of the embedded processing that we mentioned before. You can monitor and control the thermostat using a smartphone application, providing a user-friendly interaction. This is part of the user interface. This simple example demonstrates how the convergence of these technologies creates seamless and intelligent Internet of Things experience, from sensing to actuation. Each step is interconnected, enabling smart devices to adapt and respond to their environment in real time. In this slide, we'll talk about a concept or a terminology called ubiquitous computing. This is not just about just having this is not about just having a computer on your desk. It's about computing being seamlessly integrated into every aspect of our lives. Anytime communication. Imagine a world where you can connect and communicate with anyone, anywhere, at any time of day or night. This is the power of anytime communication. It removes the limitation of time zones and schedules, making interactions more fluid and convenient. Any place communication. These concepts extends beyond time to encompass location. With any place communication, you are not tied to a specific location for connectivity, whether you are at home or on the go or even in a remote location. Communication remains seamless and accessible. Anything communication. This is where things get truly exciting. Anything communications goes beyond the human to human interaction. It includes the ability to connect with devices, machines, and even other machines themselves. This is the foundation of the Internet of Things, where smart devices and appliances are interconnected, creating a network of intelligent systems. Ubiquitous computing is transforming the way we live, work, and interact with the world around us. It's creating a more connected, efficient, and personalized experience. As technology continues to evolve, we can expect even greater integration of computing into our daily lives, blurring the lines between the digital and physical world. In the next few slides, in the next two slides, we'll talk about the fundamental characteristics of the Internet of Things. So let's explore some of the fundamental characteristics that define this vast and interconnected ecosystem. First, ubiquitous connectivity. The Internet of Things transcends the traditional boundaries, connecting virtually anything to the global information and communication infrastructure. We are not just talking about phones and computers anymore. This interconnectedness extends to everyday objects, industrial machinery, and even living organisms. Second, diverse ecosystem. The Internet of Things ecosystem is incredibly diverse. It's made up of devices built on different hardware platforms, operating systems, and communication protocol. This heterogeneity uh, presents a challenge. Ensuring seamless communication and data exchange across this diverse landscape requires a robust interoperability solutions. Third, dynamic and context aware. Internet of Things devices are constantly changing their state. They can be sleeping, waking, moving, and their context, including location, speed, and environmental conditions, is always evolving. This dynamic nature requires management strategies that are This dynamic nature requires management strategies that are adaptable and flexible enough to keep up. These three characteristics shape the unique challenges and opportunities that Internet of Things present. More fundamental or continuing on the fundamental characteristics, we have massive scale complexity. The Internet of Things involves a staging number of interconnected devices, far surpassing the scale of the current Internet. This sheer scale presents significant challenges in terms of data management, network capacity, and security. Device-centric communication. The Internet of Things shifts the paradigm of communication from human-centric to device-centric. A significant portion of network traffic will originate from devices autonomously communicating with each other, enabling real-time data exchange and intelligent automation. These characteristics underscore the transformative potential of the Internet of Things, but also critical need for robust infrastructure and the innovative solutions to manage this complex and ever-growing ecosystem. In the next few slides, we'll explore the key considerations for the Internet of Things network connectivity. First, coverage area and density. Deployment scope determine the extent of your network. Will it cover a single room, campus, or even an entire industrial site? Device density calculates the number of devices per unit area. High device density requires a specialized network topologies and robust interference mitigation strategies. Second, bandwidth requirement. Data volume estimates the amount of data generated by each device and the overall network traffic. Data rate determines the required data transmission speed to meet real-time requirements and application latency needs. Data variability consider whether data transmission is continuous or occur in a burst and adjust bandwidth allocation accordingly. By carefully considering these factors, you can design an Internet of Things network that's not only reliable but efficient, but also meets the specific need of your application. Let's continue our exploration of key considerations for Internet of Things connectivity. Number 3, power consumption and constraints. Power source determine how your Internet of Things devices will be powered. Will they be plugged into main electricity, rely on batteries, or utilize alternative energy sources like solar or wind power? Energy efficiency. Optimizing power consumption is crucial, especially for battery powered devices. This will prolong battery life and minimize maintenance requirements. Number 4, spectrum availability. Choosing the right frequency band is essential. You need to consider regularity restrictions and ensure the availability of spectrum in your chosen location. Interference mitigation. Assist potential interference from other devices, environmental factors, and neighboring networks. Techniques like frequency hopping and adaptive modulation can help minimize interference and ensure reliable communication. Let's turn our attention to the critical aspects of security and reliability in the Internet of Things network connectivity. Security and reliability. Data encryption. Implementing a robust encryption protocols like AES and TLS is essential to protect sensitive data transmitted over the network. Authentication and authorization. Secure authentication and authorization mechanisms are crucial to control access to devices and data. This prevents unauthorized access and ensures that only authorized entities can interact with the network and its resources. Network resilience. Designing the network with redundancy and fault tolerance is key to ensuring continuous operation and minimizing downtime. This can involve implementing backup systems, diverse communication paths, and robust disaster recovery plans. Regulatory compliance, ensuring your Internet of Things network complies with the relevant regulations and standards. This may include FCC rules in the United States and other applicable regulations in your region or country. Prioritizing security, reliability, and regularity compliance will help you build a robust and trustworthy Internet of Things network that can operate efficiently and safely in today's interconnected world. Slide 17 presents you with a visual representation of the various communication technologies and network types used in the Internet of Things. This visual representation gives us a glimpse into the diverse communication technologies that makes this interconnected ecosystem possible. At the top, we see interplanetary networks and cellular networks, enabling long-range communication from satellites orbiting Earth to your smartphone in your pocket. Moving down, we encounter wide area networks like 4G, LTE, and 5G, providing broad coverage for devices across cities and regions. Next, we have metropolitan area networks, and local area networks. These technologies are responsible for connecting devices within a city and specify a specific building, respectively. Then we come to personal area networks. This is where technologies like Bluetooth, Wi-Fi, and near-field communication (NFC) shine, enabling communication between devices in close proximity, such as your smartphone and your wireless earbud. Finally, at the base, we have short-range wireless technologies like Zigbee, Z-Wave, and 6LoW PAN. These are ideal for connecting devices within a small area, like sensors in your home or a smart factory. This diverse range of communication technologies allows Internet of Things devices to connect and interact seamlessly, creating a truly interconnected and intelligent world. Let's dive deeper into the communication technologies and the network types that form the backbone of the Internet of Things. And again, this is an explanation to the previous visual representation, to the previous slide that has the visual representation. Let's talk about the communication technologies. Cellular technologies like 2G, 3G, 4G, LTE, and 5G provides wide area coverage for cellular connected Internet of Things devices. Think your smartphone or a smart car. Wi-Fi. This is a popular short-range wireless technology used for home and office networks, but it's also used in many Internet of Things applications. Bluetooth, short-range wireless technology, commonly used for connecting devices like headphones and wearables. Zigbee, Z-Wave, these are low power, Low-range wireless technologies often used in smart homes and industrial Internet of Things applications. They are great for connecting sensors and devices over longer distances. NFC, used for short-range contactless communication, such as mobile payment and data exchange. RFID, used for tracking and identifying objects using radio waves. Power line, this uses the electrical wiring in a building for data communication. Ethernet, a wired networking technology, commonly used in local area networks. Talking about network when we talking about network types, we have PAN. PAN is a personal area network, a network that covers a very small area, such as the space around a person. Bluetooth and NFC are examples of the PAN technologies. LAN, LAN, a network that covers a small area, such as home or office. Ethernet and Wi-Fi are examples of LAN technologies. A network that covers larger area than a LAN, such as a city or a town. Wi-Fi and cellular networks can be considered as MANs, metropolitan area networks. WAN, wide area networks, a network that covers a large geographic area such as country or even the entire globe. The internet is the largest one. This diverse range of technologies and network types allows Internet of Things devices to connect and interact seamlessly, creating the interconnected world we are moving towards. This visual representation helps us understand the different wireless technologies used in Internet of Things and how they compare across key factors. Wireless technologies. The image focuses on popular wireless technologies like Bluetooth, Wi-Fi, LoRa, and cellular networks, which are commonly used in Internet of Things devices, Internet of Things deployments. Range. It classifies technologies based on their communication range, from short-range technologies like Bluetooth and RFID to long-range technologies like LoRa and cellular. Bandwidth. It categorizes technologies based on the amount of data they can transmit, from narrowband applications suitable for low data applications to broadband technologies for high bandwidth needs. Battery life. It considers the power consumption of different technologies and their impact on the battery life of Internet of Things devices. This landscape helps us visualize and compare the different wireless technologies, making it easier to choose the right technology for a specific Internet of Things application based on its range, bandwidth requirements, and power consumption needs. In slide 20 and slide 21, I will talk about the Internet of Things sensors. I will focus in what we see in slide 20 because it's highlighting the top Internet of Things sensors. So this visual representation um, help us focus on the top Internet of Things sensors that are revolutionizing how we interact with our environment and devices. At the beginning, accelerometer sensor. This sensor measures acceleration, making it crucial for applications like fitness trackers, smartphone orientation, and even earthquake detection. We have infrared sensor. Infrared sensors detect infrared radiation, which is invisible to the human eye. They are used in wide range of applications from remote controls to security systems and even in some smartphones. We have also pressure sensor. This sensor measures atmospheric or fluid pressure. They are used in various applications, including weather monitoring, altitude measurements in aircraft, and even in some medical devices. We have also temperature sensor. These are perhaps the most common Internet of Things sensors, measuring temperature in various environments. They are used in everything from home thermostats to industrial machinery and weather stations. We have also proximity sensors. These sensors detect the presence or absence of an object in a close proximity. They are used in smartphones to turn off the screen when you put the phone to your ear, and in other applications like gesture recognition. We have gyroscope sensor. This sensor measures the rotation or angular velocity. They are used in smartphone for stabilization, in drones for navigation, and even in video game controllers. We have also motion sensor. These sensors detect movement, making them ideal for security systems, home automation, and even pet monitoring. Finally, we have smoke sensors. These life-saving devices detect smoke and alert occupants in case of fire. These are just a few examples of the many types of Internet of Things sensors that are transforming our world. From smartphone, smart home, to industrial automation, these sensors are collecting data and enabling intelligent systems that make our life easier, safer, and more efficient. You can find more sensors in the next slide as well. Let's explore the relationship between sensors, functionality, and cost. So in this table, or this table help us imagine or understand the relationship between sensor functionality and cost. As we move up the scale from low cost to high cost, we see the sensors generally increase in functionality and complexity. At the lo- at the lower cost end, we find sensors like light imaging, sensors, and sound vibration sensors. We have sound and vibration sensors. These are typically low cost, simple sensors with limited functionality. They might be used in a basic DIY projects, uh, and that's it. If we move up the scale, we encounter sensors for motion. We have motion sensors, we have velocity sensors, weather or temperature sensors. These sensors offer more advanced features and are often used in residential or commercial applications. In the mid-range, we found sensors for proximity position, flex for strain, and water treatment or flow. These sensors are typically more expensive and offer higher accuracy and precision. They are often used in industrial settings or for more demanding applications. At the highest cost end, we find sensors for chemical or gas, electrical, capacitive, pressure, load, weight, and proximity or position. These sensors are highly specialized, offering extreme accuracy and precision. They are often used in critical applications that require long-term deployment and high reliability. This image provides a valuable framework for understanding the trade-off between sensor cost and its functionality. By understanding these relationships, you can make informed decisions when selecting sensors for your Internet of Things projects. So this slide helps us understand the relationship between sensor functionality and cost. As we see, we have the cost spectrum. The image we have seen before, shows a cost spectrum ranging from low cost around $0 to $50 to high cost $150 to $1,000 plus. We also we spoke about the sensor type. Various sensor types are grouped within these cost categories. We have seen also a functionality group. Each cost category is associated with specific functionalities, such as ease of use, accuracy, and deployment scale. Lower cost sensors. These typically have simpler functionalities, are often geared towards DIY projects, and may require basic equipment or limited infrastructure, such as the light sensors, temperature sensors, and simple motion sensors. Higher cost sensors. These sensors are generally more complex, offer higher accuracy and precision, and are often used in industrial or scientific applications. They may require specialized expertise for installation and integration. Examples include chemical or gas sensors, pressure sensors, and high resolution imaging sensors. So, as I mentioned before, this image that we saw in slide 22 provides a valuable framework for understanding the trade-off between sensor cost and functionality. In the last slide, we show this diagram. This diagram breaks down the core components of how Internet of Things actually works. Phase 1, input, devices, and sensors. It all starts with devices and sensors. These are the eyes and ears of the Internet of Things, collecting data from the real world. Think about a thermostat sensing a temperature, a fitness tracker monitoring your steps, or a security camera detecting movement. This collected data is the raw material that powers the entire Internet of Things ecosystem. Phase 2, connectivity. Phase 2, connectivity. Now comes connectivity. For the sensor to be useful, it needs to transmit the collected data to other devices or the cloud. This is where technologies like Wi-Fi, Bluetooth, and cellular networks come into play. Connectivity is the bridge between the physical world and the digital world. Phase 3, data processing or analytics. Once the data reaches the cloud, it's time for data processing analytics. This is where the magic happens. Software analyzes the collected data, looking for pattern, trends, insights. This could be anything from predicting weather patterns, from predicting weather patterns to optimizing traffic flow. Finally, phase 4. Phase 4 is all about the user interface. This is how the user interact with the Internet of Things system. It could be a smartphone app, a dashboard in your computer, or even voice-controlled assistant. The user interface allows you to access the data, control devices, and ultimately benefit from the insights gained through the Internet of Things. So there you have, from sensing to analysis to action. This is how the Internet of Things works. It's a complex yet fascinating ecosystem that's transforming the way we live, work, and interact with the world around us. And thank you for listening. This is the end of part 1. I will be publishing part 2 of the introduction of Internet of Things. By the way, these slides are also published in Canvas under module 2.